Maggie is a computer scientist. She is an expert in AI and machine learning. And we've been working with Maggie for the last couple of years on a number of different big data sets that we have and big pain problems that we have that we're trying to have Maggie help us think about how we might be able to analyze. I like sort of personalizing my comments. One of the couple things that I like the most about Maggie is, number one, she has unusually good communication skills for a data scientist.
Thank you.
I mean that in all the best positive ways. And then more importantly, I think, is she really tries to understand the social context of the data she's analyzing, and it's super important for her to be taking on, to be working with problems that are socially meaningful. So the first time I met Maggie, she had done this extensive literature search in chronic pain, but she tries to dig in. No, she really tries to dig in and understand the problem before she starts analyzing data. And so anyway, those are both unusually good attributes for a data scientist working in team science.
I think what Dan is trying to say is that I slightly creepy stalked him before meeting with him. That's the more honest way of saying it. All right. Okay. Cool. We're on. It's a miracle that I was able to put this up. All right. Okay. I am acutely aware that I am the graveyard shift. I am between you and dinner. So this presentation of how machine learning can be used in pain research will be short and higher level. And what I'm going to present is not an exhaustive list of all the things that we can do using machine learning in pain research, but it is selectively biased towards newer things. So I won't be presenting the classical machine learning approaches. I will kind of be maybe presenting that very little and then jumping onto here's the newer, like sexier thing that the machine learning community is talking about and how can we use this for pain. So hopefully, by the end of this talk, you will know a little bit about what machine learning can do in the area of pain-related research, and you will hopefully know some of the different types of deep neural networks and what are some of the problems that we might face if we are doing research in machine learning, and how can we use these methods to answer questions of a causal nature. This is a big spread. There's a lot of different concepts, and we're going to be jumping around a little bit. In the off chance that you zone out for a little bit, look for a slide that has this warning sign and says TLDPA, stands for too long, did not pay attention. So these slides will hopefully summarize what you just missed, and after these slides, we will be jumping into a new topic. So as to not get lost. Obviously, off chance that this happens. Okay, so there are, roughly speaking, two sets of machine learning of questions in pain that we can answer using machine learning models. The first set is the set of predictive models, and the second set is a set of models that help us answer questions of decision support. So in the predictive bag of questions, what we're really focusing on is we want to reason about the world as it is. So nothing is going to change drastically, but I am trying to develop a model, to build a function that helps me predict some outcome in the future, or it helps me identify some diagnosis, some ailment that happened in the past. So the word prediction is a bit of a misnomer because you could be looking at things that have already existed, but you're trying to detect these diagnoses in that case. The most commonly used set of machine learning tools that we can use to answer these questions of prediction, not the only, but the most commonly used one is supervised learning. On the other hand, if I am trying to build a machine learning model that will be used to support a decision or an intervention, what I really want to reason about is what happens if I change the world, change the universe, change the state of the patient by making a specific intervention. So I'm no longer reasoning about the most likely outcome. I'm now reasoning about what is an outcome that I can observe if I change the course of the universe in a specific way. And this type of questions focuses on estimating the causal effect of this intervention. So what is the effect of this intervention on a specific outcome that I'm interested in? Or telling us what is the best course of action. So instead of trying to identify exactly what the effect is, I just want to know which one is best, which intervention is best. And the most common machine learning tools that we use for this set of questions is either causal inference tools, machine learning-based causal inference tools, or reinforcement learning. We won't be talking about reinforcement learning today, but I will talk, hopefully, a bit about causal inference. So we will talk mostly at first about prediction, and then we will move on to decision support. Jumping right into it, what is the set of tools that I just referred to? What is supervised learning? So in supervised learning, my goal is to predict an outcome or detect a diagnosis for a new patient. So a new patient walks into my clinic, I want to use this function to detect whether or not they have this ailment or predict if in the future they will experience a negative outcome of some sort. For example, maybe I want to use fMRI images to predict a type of pain, like is it nociceptive, is it neuropathic, what type of pain is this patient experiencing? That's one style of questions that we might think about. And what we want here is to take my inputs, my fMRI images, pass them through some function, some machine learning model or machine learning function, so that it gives me the predicted pain type. Similarly, we might be interested in, I want to take the patient's medical charts, like their clinical notes. And I want to use those clinical notes to predict whether or not this patient is going to get an opioid in this hospitalization. That's another style of questions that we might want to answer. Or a third type of question might be, I want to take electronic health records, or what we sometimes call structured data. So you can think of it as organized in columns, and every column means a specific thing. Like it's vital signs, it's medical history. That's what I mean by that. And maybe I want to take this data set and use it for patients who've just had a surgery to predict what is their postoperative pain. One common thing across those three examples is they're all using an input to predict a specific label. That is kind of the hallmark identifier of this is a supervised learning method. I have something very specific that I want to predict. There's this very specific label that I'm interested in. So in order to do that type of learning, I need my data set to be organized in pairs. The input and its corresponding label. So one fMRI and its corresponding pain type. Or one clinical note and its corresponding whether or not that patient got an opioid. So that's what we need in order to train these models. And if you will notice, these models are very diverse. Like they take very different inputs. So it could be text, it could be images, it could be these kind of like structured data sets. Okay, so how do we get these nice functions? It's simplifying it a little bit. It's 2 steps. I'm going to, as an analyst, define a set of suitable functions. And we will talk about what suitable functions are in a second. And I'm going to try to identify, using my data, what is the best function out of this suitable set of functions that best fits my data. And we will see what that means in a second. So we want to define what is a set of suitable functions. The set of suitable functions will depend on the type of the problem. So it does look very different if I am, or the set of functions is very different if I'm modeling image data versus text data versus these structured data sets. And let's start with the simplest possible one. Let's say we're looking at structured data. For simple enough functions, for simple enough relationships, as an analyst, as an expert in the field, I might know enough to define what is a set of suitable functions. So let's say I am trying to predict postoperative pain based on preoperative pain. And let's say that an expert in the field of pain told me that the relationship is linear. Then one possible function is to kind of model the postoperative pain as a linear function of the preoperative pain. That's one possible function. But it could also be a function that's steeper. It could be a decline, like it could be an inverse relationship as preoperative pain increases, postoperative pain decreases for some reason. All of these are viable functions that I could use to represent the relationship between preoperative pain and postoperative pain based on expert knowledge. Now, what happens in settings when it's not straightforward how your inputs relate to your outputs. Like when my inputs are text, or when my inputs are pixels, or even when my inputs are structured data, but it's higher dimension. What do we do in these cases? These are the cases where machine learning tends to be useful. But if we already know a lot about the function, it might not be worth using machine learning. So if I don't know the shape of the relationship, one solution, and this is not all the solutions, this is one set of solutions, is to use deep neural networks. There are a lot of other really great methods that work, and sometimes they work equally well, but again, I'm looking at the kind of newer things in this talk. So if my input is an image, is image-based input, like an fMRI, we typically use what we call convolutional neural networks. If my inputs are text-based, we either use recurrent neural networks or transformer-based models. Before getting into what all of these mean, it might be helpful for a second to just talk about what's a deep neural network. So this is where props enter. So let's say that you are training or estimating a logistic regression. We can think of this Lego block as, this is our logistic regression. It takes some input, which is our patient characteristics, and it outputs some probability. You can kind of ignore all the other ridges. I have one output here, and that is the patient probability. In its very simple form, the very basic type of deep neural network operates somewhat similarly. It's this on steroids. What we're going to do next is or we do in deep neural networks, the most basic form, is I'm going to take something that looks like a logistic regression, and on top of it, I'm going to stack another logistic regression. So I started with one logistic regression. It has many different outputs, and I'm going to use these outputs as an input to another logistic regression, and I'm going to stack maybe another layer of logistic regression on top of it. And finally, I'm going to end up with what we call the head of the model, and that's the one that spits out my final prediction, and then we're done. So that's roughly speaking what the general structure of a deep neural network. A lot of places people will kind of, when they're introducing deep neural networks, they will talk about how it relates to the human brain. All the respect to those people, I do not understand it this way. I think of it as Legos, so hopefully that was at least illustrative. Okay, so again, this was the very basic form of a deep neural network. When we play with more complicated neural networks, each one of these building blocks gets a little bit more complex. It stops being similar to a logistic regression. It starts being more complicated. It has more computations to it. And we will talk about these building blocks if I am using input as an image or if my input is text. So if my input is image, this building block is called a convolutional layer. This convolutional layer is special because it is able to pick up on specific properties that are very specific to images. For example, in images, the spatial locality of my inputs is meaningful. So I think all of us can look at this and be like, okay, this is a human brain, most likely. I think this is a human brain. Every location of every pixel is meaningful. So if I take some of the pixels like from the ventricles and swap them with the medial frontal cortex, this no longer looks like a human brain. This looks like something weird. So there was information in the location of the pixels, and convolutional layers are really good at picking up that spatial information. Another property of images that is very unique is translation invariance. So I take a brain, I shift it a little bit to the right, it's still a brain. So that should be something that my model identifies. If I take the image of the brain and flip it, rotate it 180 degrees, the model should still be able to pick up on this is a brain. And in principle, convolutional layers do that. Okay, so that was images. Now text. If you've not been paying attention to the news lately, this is the golden era of modeling with text data, so this is it. As of 2017, 2018, the normal thing to do was to use a recurrent neural network to model text data. Recurrent neural networks are really good, again, their building blocks are really good at capturing recurrent structures, meaning in normal text, you have subject, verb, noun. So RNNs are really good at picking up, okay, if my input has a subject and a verb, the next likely word is going to be a noun. Or recurring themes like toxicity, like sentiment, things like that, RNNs are really good at encoding. In principle, they can tolerate dependence on long texts. For example, in this text, it says, I'm originally from Egypt, currently I'm living in Ann Arbor, and then a lot of yakking on, like a lot of text. And then at the very end, this person says, well, my native language is what? How do I predict that? How does the model predict that? In order to predict that, it needs to have incorporated that at the very beginning of my long paragraph, I said that I was Egyptian. So what follows should be Arabic. So that's what I mean by dependence on long sequences. And in principle, it can handle arbitrary lengths of an input. Like you can feed it a book, and it will be able to process the whole book. These RNNs worked sequentially, by processing sequentially your input. So it reads the first word, it learns something about its input. It reads another word, it learns something about the input, and so forth. And because of that, it had some limitations. The first is that it was incredibly slow. And the second is that it actually was very prone to forgetting over very long sequences. I don't like anthropomorphizing neural networks, so by forgetting, the technical term here was vanishing gradients, but you can think of it as it was not able to recover previous information that it saw a while ago. Okay, then what happened? Then in 2018, tectonic shifts. In 2018, there was a paper that introduced the concept of transformers. Instead of processing word by word, transformers take in the whole text as an input. And then they basically decide which parts of that input should I pay attention to. This is the building block of ChatGPT, for example. A good intuition that you can have here is RNNs are the equivalent of someone sitting down and reading through a book from end to end in order to learn more about some concepts. Whereas transformers are equivalent to a person, or are analogous to a person sitting down and looking at the table of contents and saying, well, okay, I want to learn about this specific concept, so I'm going to go to this specific part of the text and extract information from it. So that's kind of an analogy to keep in the back of your mind. I'm going to very quickly go through the intuition behind these attention mechanisms and these transformers. If nothing else, if you're in a party soon and someone says, oh, ChatGPT, transformers, attention, you might know some of these keywords. Okay, so I think it's an intuitive way to think about what these transformers are doing is to think about a search problem. So think about entering a search query into, let's say, Google. And let's, for the sake of simplicity, say that there are only 3 possible answers. The first step in a transformer, what it does is it encodes almost like the gist of those 3 answers. And you can think of those keys that we're learning as what I would include in the table of contents. So that's like the table of contents entry for this specific answer, for the first answer, for the second answer, and for the third answer. And what we're going to do next is we're going to compute how similar is this key, or is this gist of my answer, to the query. So if you look at this, you'll see like the first the first item that we get back in search is not very relevant, neither is the last one. The second one is really the thing that is relevant to learning about attention in neural networks. So once we've identified that the key to my second entry and the query are most similar, I'm then going to learn some value, some information about the second answer. And you can think of this as, now I've gone into that chapter and I've like summarized it for myself. That's the value. And that's the answer that we're getting out of the transformer, or in this analogy, that's the answer that I'm getting out of my search. So I'm going to extract the value that has the highest similarity or the highest attention score compared to the query. Okay, we just, like all what I've just described, whether it's for CNNs or transformers or RNNs, that's one of these blocks. So how many do you stack them? How wide do they have to be? All these design choices, you can certainly go in and like hire a graduate student or hire a data analyst and kind of try to figure out the best architecture, by architecture I mean like this building here, I've chosen 3 floors in my head. So how do I choose my architecture for my problem? You can certainly try a bunch of things. That's not what we do in kind of on the machine learning side. What we do is we know there are specific predetermined architectures that tend to work. For image data sets, we tend to use, or at least start with, dense nets and res nets. These are just commonly used architectures. For transformer-based models, Clinical BERT and PubMed BERT are specifically made to digest clinical text. But more generic ones are BERT and Llama. Llama is Facebook's model. Again, there are other models that I didn't cover here that are really great and have sometimes better performance than deep neural networks. So if you're interested, I'm happy to answer questions about these later. All right. Our first too long did not pay attention. We just talked about supervised learning. That's one approach that we can use to create predictions for our medical data. If I don't know the nature of the relationship between my inputs and what I want to predict, it's a safe bet to use deep neural networks. For text data that is RNNs or more modern approaches like transformers, for image data, it is convolutional neural networks. How do I pick the best model? Well, the first thing that we need to agree on is these blocks in real life, these are matrices. So matrices that have numbers in them. So how do I pick the best configuration of these matrices? What are the values of these matrices? We pick them by defining something called a loss function. And this loss function will tell me, for an arbitrary model, how good does that model perform? So how well does it allow me to predict my target label? And we're going to use, or it depends on what kind of problem we have. If our outcome is binary, you can use something called the misclassification rate, which just counts how many times am I wrong versus how big is my data set. Or if your outcome is continuous, you can use something like the mean squared loss, which measures the mean squared distances between my inputs and, my target labels and my predictions. And then what I'm going to do is I'm going to define an optimization algorithm. This optimization algorithm just says, find me the best values for my matrices such that my loss function, so how bad my model is minimized. I want the best possible model by minimizing the loss function. This one was short, but what we just covered is, in order to pick our model, we need a loss function and we need an optimization step. That's sort of how we get from data to model. All right, so that was supervised learning. I wanted to go over some common challenges and the remedies. We'll see how far we get because I'm running a little bit tight on time. One problem that we can run into is if our data is small, but our model class, the set of suitable models that we've picked, is too rich, it is too complex. One problem that we can run into is our model memorizes our data. A model that memorizes your data is going to be useless for your new patients because it has not seen these patients. These patients are not represented in your development or training data. So we want to avoid that problem of memorization. The classical way of dealing with this in classical machine learning is regularization. So I'm going to try to limit the expressivity of my model somehow. And I'm going to pick how much I limit this expressivity. I won't go into the details of this, but I'm happy to answer questions about it if you have any. In deep neural network world, what we've been doing a lot more is pre-training. So at its core, pre-training is saying, I don't have a big enough data set. I'm going to borrow strength from another data set, a large data set that maybe exists. I'm going to borrow strength from that data set to learn some patterns, And then I'm going to tweak it for my own problem using my small data. So, for example, if I want to use fMRI images to predict type of pain, maybe I have access to another data set, and this is a large data set. They didn't measure pain in this data set, but they have a lot of fMRIs. So one thing I could do is I could take their fMRIs, learn a function that predicts some label that they have in their training data, like patient age. That's one way to do pre-training. But a lot of times these large data sets don't even have any labels. Like I don't even have a label that I could predict from my large data set. So what you can do here is learn to reconstruct the image. So if I just have fMRIs, I can learn a function that reconstructs the fMRI image again. The hope here is that my pre-training function will learn something about the patterns that exist in a human brain that will then be useful for my problem. In the context of text, and this was one of the reasons why ChatGPT kind of like was very successful, is you can use text data that has no labels at all by masking some words in your text and asking the model to recreate this text. So here in this example, what does it say? It says something, the patient presented to the ER complaining of lower back what? You ask the model to fill in that blank. In doing so, it turns out that the model is actually really good at capturing common sentence structures that we use to communicate in typical text. Of course, when your pre-training data is the entire internet, like all the text on the internet, you can really learn very rich models, kind of like the ones we see in ChatGPT. So I've pre-trained, great, now what? Like I've gotten some model that is pre-trained on this large data set. Now remember that these functions are all like under the hood, they look something like this. They're a collection of stacked on top of each other building blocks. So one thing we can do is we can take the top part of the model off and say, okay, I'm going to build just a small part that sits almost on top of my existing big model, and I'm going to specialize this block for my specific problem. So if this part of the model was trained to predict patient age from fMRI data, I'm going to take the last part and then I'm going to add on top a specialized layer that takes whatever I have from the pre-training data, but now it predicts pain, not age. That's one way to do it. Another way to do it is to say I'm going to tweak all of my model. I'm going to fine-tune or update my entire model based on my new data sets. So of course, if you have a larger data set, you can afford to fine-tune the whole thing, but if you have a very small data set, you might not be able to afford anything other than like the top part of the model, basically. I really wanted to show you what in-context learning is, but I'm running tight on time. So I'm just gonna put it up there that this is the rage now. If you're interested, I encourage you to like go look at what in-context learning is, but that is one of the things that our community is currently kind of going obsessive about. Sorry, it is cool, but the time is tight. All right, there are some other challenges that we might face, and I think these are important to kind of stop at and discuss. In a lot of cases, our models might pick up on what we call shortcuts. Shortcuts are patterns in the data that are easy to represent, but they are only spuriously correlated, not causally related to the target outcome that I'm interested in. For example, if I want to build a model that takes in human faces and predicts if they're grimacing, predicts if they are in pain, if all my labels have been provided by white people, and they cannot recognize pain in a dark-skinned person, then I'm going to end up maybe labeling all the dark-skinned individuals in my data set as no pain. And then what my model is going to learn is it's going to learn, if you give me an image of a person with a dark skin, I'm going to predict that they have no pain. So it really has learned to encode the skin color as a predictor for pain or not. So if I give it an image of a patient who is in pain, but they are dark-skinned, it will not detect it. But a white person, they might be able to detect it. So that's an important problem, and we've actually, in some research that didn't have the time to go over, we're finding similar patterns in text data. Stigmatizing language is very predictive of whether or not a person gets prescribed an opioid. We're seeing these different race-related patterns because people of specific races maybe are more likely to have stigmatizing language in their clinical notes. So what do we do with this? One of the solutions is to explicitly penalize encoding information about the shortcut. In this example, it's race. So I ask my algorithm to give me the best model that gives me the best prediction, so minimizes my loss, but also I'm going to say, find me the model that gives me the best predictions, but also does not depend on race. There are a lot of complications here, but that's sort of the basic idea. Okay, too long, did not pay attention. We talked about a couple of challenges that might arise in the context of using clinical data and deep neural networks. One is small data, and we can remedy that by doing pre-training, followed by linear probing or fine-tuning, or in context learning, which we didn't go over. Shortcut learning, we can remedy by doing this invariant learning, where we ask the model to not depend on any features that are correlated with, let's say, the race of the patient. Okay. The last part we're kind of going to blaze through because, again, I am acutely aware of dinner. So we're going to talk a little bit about how machine learning models can help us answer causal questions. Hopefully, we are all in agreement that correlation is not causation, and everything that we just talked about, that is encoding correlations in the data, not causal relationships. So when we're asking questions about causality, we're focusing on estimating the change in outcomes due to an intervention. At its simplest form, we would be asking, what is the outcome for this patient if I give them treatment A versus treatment B? The difference between those two outcomes is what I am interested in. A related topic, but not identical, is the topic of reinforcement learning. Reinforcement learning does not care about the causal effect itself, but it cares to tell us what is the best course of action. The fundamental problem of causal inference is, if this is my data set, and I have X number of patients, and let's say I want to learn what is the causal effect of high OME, oral morphine equivalence units, on patient-reported pain after they have gone through an operation. So does intraoperative OME matter for postoperative pain? What I want to learn is, what is the pain if I give them high OME minus their pain if I give them low OME? And in order to calculate that, I need to know what is the pain if I give them high OME versus what is the pain if I give them low OME. So let's look at the first patient. She got high OME. So if you look at, let's see, I don't really have a pointer. Okay, for the first patient, she did receive high OME, and our observed pain for her was 4. So I know what her pain is if I give her high OME. I observed that. But I do not know what is her pain if I give her low OME. Similarly for the other two patients. For them, I did not observe high OME, so I can only tell you what their pain is if I don't give them high OME. But I have no idea what their pain would be if I gave them high OME. How do we remedy this problem? The problem that the thing that I'm trying to model is never observed. How do I remedy that? We remedy that by asking for a certain set of assumptions to be satisfied in our data set. I'm going to go over the first two. The third one is not that important for our purposes. The first one is no hidden confounders. So there needs to be no variable that I didn't measure that affects both the treatment and the outcome. I need to have measured all the variables that affect those two outcomes and treatment. Positivity of overlap is that there is no group that receives the treatment 100% of the time or 0% of the time. In other words, I can't estimate the causal effect of not giving someone penicillin if all they've observed for that group is they've always gotten penicillin, or the other way around. Consistency is not that important, so we're gonna skip over it. I know this slide is titled A Naive Approach, but looking at time, we're probably only going to go over the naive approach. But there are smarter ways to do this. So one thing we can do, uh-oh, I broke something. All right. The other one. Okay, all right, sounds good. Oh, perfect. This one's on, so we're good, I think. All right. All right, we're gonna just ignore it. So one thing we can do, if these three assumptions are satisfied, is I'm going to take my data set, and I can split it into two. One where there are patients who receive the treatment, and the other with patients who do not receive the treatment. And I'm going to use the first part, like the data for the group that did not receive the treatment, to learn some function that takes me from patient characteristics to the outcome. And I'm going to do the same for the second group. Learn a function that takes me from their characteristics to their outcome. In comes a new patient. I'm going to apply my first model to get that patient's outcome under treatment and apply the model for the non-treatment outcomes to that same patient, get the predictions from each of the two models, subtract them, and that would, roughly speaking, give me an estimate of the causal effect. If our assumptions are satisfied, and as our data becomes really, really, really big, that approach is typically reliable. There are problems with this approach, but I won't kind of dig into it. I will just end by telling you quickly of some work that we're doing here where we are trying to look at postoperative pain and how intraoperative opioids affects postoperative pain. So we want to know if I give patients high opioids during a procedure versus if I give them opioids, low opioids during a procedure, what is the difference in outcome? And the outcome here is 2 hours postoperative pain. Some inclusion-exclusion criteria. I'm happy to talk about these offline. The thing that is interesting that we're finding, and this is still very much work in progress, so take this all with a grain of salt, is that about 20% of the population experiences a paradoxical effect, where their postoperative pain increases if you give them an opioid. So what I'm going to show you here on the x-axis is patient ranking. So how high or low do they rank according to their estimated causal effect. And on the x-axis is how high or low is their observed change in pain. So on the left side of the screen, these are patients who benefit a lot if you give them an opioid. And on the right side of the screen, this is patients who do not benefit. Actually, they experience a worsening effect in pain if you give them an opioid. Every one of those dashes, gray dashes, is a patient. And the red dashes are patients whose causal effect is statistically significantly higher than 0. So there's a statistically significant increasing of the pain if you give them an OME. And I'm going to do the thing that Adrian does not like. Sorry, Adrian. I'm going to show you some of these regression coefficients. What are the factors that affect this paradoxical response? So some of the things that we found is some of these chronic pain conditions are popping up as factors that are associated with this paradoxical effect, so including IBS and fibromyalgia. There are other factors that don't quite make sense yet, but again, this is work in progress. But also the interesting thing is that if you look at the factors that are protective, also some of them include chronic pain conditions like migraines or bladder pain syndrome. So again, we're still trying to figure out who this group is, but what I can say from running this analysis multiple times is that this group definitely exists, and it is worth kind of studying who they are. Final thoughts. If you're interested in following more work in machine learning and healthcare, there are a couple of venues or publication places that originated in the machine learning community but use a lot of machine learning. These are the places that I would go to if I want to learn about what are the novel things in machine learning that are related to healthcare, including Machine Learning for Healthcare, Conference on Health Learning and Inference, and AMIA or JAMIA. These are a couple of places that are good to look at. One question that I get a lot from my collaborators is how many data points do you need for this? I think it's so unsatisfying of an answer, but unfortunately the machine learning community doesn't quite focus on power analysis. Like the classical power analysis just simply doesn't exist in the same way in the machine learning community. Because at its core, what we're trying to do is you give me a data set and I will give you the best that I possibly can. Rather than there is a truth out there and I'm going to use this data set to recover that truth. That's a different paradigm, and it requires assumptions that do not exist in machine learning. So doing power analysis in machine learning is very, very difficult. And I know this is something that matters a lot to folks who do clinical care. Another thing that I have noticed by sitting on panels, NIH, NSF panels, a lot of the grant proposals kind of get shut down because it's a very elaborate, very complicated machine learning model that is answering a question that is not clinically meaningful at all. So the kind of thought process of I'm going to build a very big hammer and try to find a nail to use that hammer on is typically not a very successul strategy, or I've seen it not be very successful. So I think it is important in all these interdisciplinary collaborations in team science, right, to kind of start with, here's the clinical questions that we're interested in. Maybe a method off the shelf can answer that question. Unlikely, but maybe. So starting with the clinical or the application question first tends to be a more successful strategy, in my opinion. I'm going to stop here, and I don't know if we have time for questions.
We do have time for questions.
Okay, great.